degradation of surface roughness due to cyclic loading. The content I'm covering in this presentation includes introduction of objective key characteristics in degradation process, review and comparison of models, modified equations, discussion and conclusion. The first part is introduction. A rope joint can be defined as a brittle fracture in ropes along which little or no displacement can be observed. And the rope joint is widely existing in rock building and has significant effects on the mechanical behavior of rock masses. And in the service life of rock structures, they may suffer cyclic loading due to weak earthquakes, for example, and this process would change the property of rock joint and hence influence the behavior of rock masses, such as shear stress and shear stress. And the change in shear stress mainly arises from the degradation of rock joint surface. And in the design, we know we need to ensure the shear stress is not exceed the shear stress. However, the complex mechanism of degradation of rock joint make it hard to predict shear stress of rock joint on the cyclic load. So the main objective of this research is to review and compare the existing model under both constant normal load and cyclic loading condition, and the constant normal stiffness and cyclic loading condition, and then modify the equation in order to improve its accuracy and flexibility. To better understand the existing model, it is necessary to understand the key characteristics in the degradation process. And there are two cycles that need to particularly consider, the first cycle and the final cycle. Because these are two most possible cycles that shear stress may exceed shear stress. The peak shear stress always appears in the first cycle, and this is because the second order, which refers to asperity with low angle and length, would almost totally degrade in the first cycle, and this process leads to high shear stress. And in the final cycle, although the shear stress is lower than other cycle, the shear stress of rock joints in final cycle would also decrease hugely compared with the first cycle. As the most second-order asperity has degraded, the first-order asperity becomes the main factor influencing the behavior of rock joints after the first cycle. And the shear stress of rock joint under both CNL and CNS conditions decrease with the increase in the number of cycles, joint roughness coefficient, and the initial normal stress. And just shear stress of rock joint under CNS condition also increase with the increase in normal stiffness. And those findings are helpful for me to evaluate the existing model. The next part is review and the comparison of models. Many studies try to build an empirical model to predict shear stress. And here is an example. They use multivariable regression algorithm to build the empirical relationship. A great deal of data is used to build the equation. And the red line in figure 5 demonstrates the shear stress at each moment. However, it can be noted that sometimes the predicted results is clearly lower or higher than experimental results. The advantage of this model is that it can predict shear stress at any moment. However, this model are not able to reflect the influence of asperity degradation, and it is not fit for rock joints with other GRC values, and the accuracy is not good. And here is a semi-theoretical models proposed by Ma. As shown in the right, the shear stress can be easily acquired by if we know the vertical stress and the dilation angle. And this study proposed a way to determine modified angle based on the model proposed by Barton in 1989. According to the experimental results, the ratio of mobilized GRC value and the peak GRC value is determined, and the sum of value is true in table 1. And the advantage of this model is that the predicted result is close to experimental result, and the model can predict shear stress at any moment. However, this model do not investigate the relationship between the change in the mobilized GRC and the initial normal stress, as the ratio between mobilized GRC value and peak GRC value is different in different cycle. Hence, we need to calculate this ratio for each cycle, which is a huge job. Besides, this model does not provide the method to determine mobilized GRC for certain conditions. Therefore, this model does not have any useful purpose. And here is another theoretical model proposed by O. He put forward a new method to determine modified dilation angle. In this equation, the modified dilation angle is related to number of cycles and the initial asperity angle. The advantage of this model is that the predicted results are close to the experimental result, and the model can predict shear stress at any moment. And it is suitable for root joints with other GRC values. However, the disadvantage is that it is hard to determine initial asperity angle for real root joints. And in conclusion, the Hayes model has low accuracy and appreciation, and it cannot be improved to improve its performance. And the Mars model has high accuracy and low appreciation. But if we can find the method to determine mobilized GRC value, the appreciation of this model can be improved. And for OS model, it shows high accuracy and high appreciation, but we still need to check whether it's accuracy. So the next part is modified model. I choose to check and modify the model proposed by Ma. For this model, if we know the GRC mobile value for certain condition and the relationship between the change in GRC mobile value and other factors such as initial normal stress, peak GRC value, and the resting diffraction angle, we can predict shear stress. And at first, I investigated the relationship between initial normal stress and the ratio of GRC, mobilized GRC, and peak GRC value. And this is the data used to investigate the influence of initial normal stress, which is acquired from Hayes research. So I calculate the ratio of mobilized GRC and peak GRC in the first 3 cycles for 3 different levels of initial normal stress. As shown in figure table 4 and 5 and 6. And then I noticed that it was when root joint having maximum shear stress, the increment of value of the ratio of the mobilized GRC and the peak GRC is same when initial normal stress increase proportionally. Like this, when the initial normal stress is increased from 2 to 4, the ratio is increased by 0.006. And when increased from 4 to 6, the increment of the ratio is also 0.006. And hence, I built equation for each cycle and acquired this graph. This graph can be used to determine the ratio for this root joint. And the calculation below below shows that experimental results are extremely close to the calculated results, which is and then I invested the relationship between the ratio and the picture stress. And the data is acquired from the Leeds research. The first step is also calculate the ratio for each cycles in different GRC. It was found that for a loop joint with a certain GCS and a residual frequency angle, the ratio of mobilized GRC and peak GRC value decrease linearly with an increase in GRC, the peak GRC value. So it can be, I built those three equations to predict uh, the ratio for yoke joints with different GRC value. So based on these two findings, an empirical model for mobile GRC uh, can be proposed. When for the yoke joint with GCS value is 72 and residual fraction angle is 35, the 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 ratio can be presented as this equation. This equation consists of three parts. The first part represents the ratio when stiffness is 5 and GRC is 13.2. And the second part represents the influence of stiffness. And the third part represents the influence of peak GRC value. So as a conclusion, those two findings, I found two findings in this research. The increment of the value of mobilized GRC and peak GRC value is safe when initial normal stress increase proportionally. And for a loop with a certain GS and residual frequency angle, the rate of GRC mobilized and the peak GRC value decrease linearly with the increase in peak GRC. These two findings are helpful building model for loop joints with other GS level. And the proposed model can only be used to predict shear stress for loop joints whose GS value is 72 and residual friction angle is 35. So the limitation of this model is big. And this model may not applicable for loop joints when the initial normal stress is over 6. That's all about my presentation.